But it's very important, I think, that every anesthetist has a grasp of how this is calculated. And this also allows us to understand the amplitude, so that it's not simply a little bit of a greenhouse gas, but that we understand the amplitude and why certain habits are much worse than others. You could also call it a PD course about our ecosystem. So, so we all know, of course, as a short introduction, that our ecosystem is changing, that the climate is heating up, and that views like this more and more look like this. Last summer was terrible for our planet. And not only for the forests, not only for ice sheets, but we see that even the ocean currents are changing. The ocean is heating, resulting in much more severe weather events, destruction of marine ecosystems also, and even that because of changing precipitation, even in the mighty Amazon forest, large parts are drying, burning, and changing in much more rich ecosystems. So this is only the beginning of something else to come. And this is why we need to act. The most obvious thing we see now already, obviously, is the melting of the ice sheets, with also, obviously, local terrible effects on the ecosystems. So what happened the last 50 years already, which is only a taste of what's going to come. This is a small increase in global temperature. As you can see on this graph, this is not in every location the same. Particularly in the North Pole, the increase is much higher than other parts. But if we want to know what can be the effect of only a few degrees warmer, we simply have to look at the Sahara Desert, the largest desert on the planet. 12,000 years ago, this was the ecosystem of most of the Sahara Desert. You see there on the left drawings that people drew on the rocks. So these animals are not what we are used to see now in the Sahara Desert. So only 2 degrees difference makes the difference in ecosystems between this and this. And this is only the beginning, because a small increase in temperature, for instance, caused by emissions by humanity, will have many positive feedback loops that amplify this effect even more. For instance, when a small increase makes the snow cover to melt, then a white surface is replaced by a darker surface, capturing more heat of the sun. Also, permafrost thawing causes billions of tons of CO2 and methane gas to be released, amplifying the greenhouse effect that we have started. And also, for instance, the forests in Canada and in Siberia, because the winters are less severe, many insects can move to the north and destroying many of the trees that are not used to these kinds of beetles, for instance. And this makes that forests of millions of acres are dying. And then after a few years, all these dead trees are very vulnerable for forest fires. Obviously, this is what we have seen this year, for instance. So many positive feedback loops that we really don't want to activate, actually. So this is why scientists declared a few years ago that we are living in a climate emergency, and we are going to say so. And we, as clinicians, as doctors, we all know what an emergency means. In the emergency room, we don't make plans for next month. We have to act immediately, or the patient dies. So also in this case, we don't have time to act within 50 years. We need to act immediately, or it will go terribly wrong. But of course, this is a terrible message, but what has this to do with anesthetists? We all know a little bit, of course, but volatile anesthetics are extremely potent greenhouse gases. And depending on our habits, one anesthetist can easily emit more greenhouse gases than 100 average Americans in a year. So to better understand this and how this is quantified, we have to take into account a little bit of climate science. So this is our planet, of course, and we have a temperature that is quite fit for life, about 20 degrees Celsius on average. But this is not so obvious that this is the case, because when we look from a distance, actually we live in an extremely cold environment. And when we look the other way, it's an extremely hot environment. And we are just in between. But also the moon, for instance, is just in between. And the moon has a comparable average temperature than Earth. But you see that the extremes are much more severe, making it very unsuitable for life. We have, luckily, the atmosphere, which buffers everything and makes it livable. Because all the energy obviously comes from the sun as electromagnetic radiation, going from the very short wavelengths up to the much longer wavelengths. And all this energy is emitted because the sun is hot. And the first one to describe the relationship between the temperature of a body or of an object and the radiation was Max Planck more than 100 years ago, who showed that an object of the temperature of the sun, for instance, it's this orange curve, emits energy and light as visible light, a lot of ultraviolet light, and also a lot of infrared light. And on the other hand, a much colder object like us, about 20 degrees Celsius, or the temperature of the Earth, 300 Kelvin, also emits light, but only in the infrared range. And this is very important to understand the greenhouse gas principles, because this is a picture of NASA who shows the fluxes of energy through electromagnetic radiation. And normally, when everything is in equilibrium, the amount of energy coming in and going out is exactly the same. And thus the temperature remains stable. But we see here that the yellow arrows, so all the energy coming from the sun is around visible light mainly. All of it comes from the sun. A little part of it is absorbed by the atmosphere. A little part is reflected on the clouds. And then it reaches the soil, of which again a little bit is reflected, mostly on snowy areas. And then the Earth heats up. And then because the planet is hot, it emits also its energy as electromagnetic radiation. But in this case, it is infrared light. And you see the very thick red arrow. But then you see that the arrow almost disappears in the atmosphere. This means that almost all the radiation energy is turned back into heat. So heating up the molecules in the atmosphere. And then this hot air again emits its energy in all directions, part of it down, part of it up. And eventually you see that the energy can turn a few times up and down before it escapes to space. This was always the case, but since we have added greenhouse gases, so we have increased this part where infrared radiation is turned into heat, the equilibrium is disturbed, and at this moment a little bit of what goes in remains in, and we have a constant flux of about 1.64 watts for every square meter of surface on the planet. And of course we have a lot of square meters. So this is a lot of energy. We know this very precisely, that this is exactly 1.64 watts per square meter on average, because of the Discover satellite launched in 2015 that can observe the Earth in all the wavelengths, and therefore can measure exactly how much energy comes in and goes out. So this is a number that's having a great effect. Because of the total solar energy coming in of about 173,000 terawatts, only, let's say, 836 terawatts remains in the air, on the planet. So this 836 terawatts is 836,000 gigawatts. So we are heating the planet at a rate of about 836,000 big nuclear power plants. Or said otherwise, this is 46 times the total human energy use, or the equivalent of exploding 13 Hiroshima-type nuclear bombs every second. So a lot of energy. This is obviously not sustainable. We cannot keep on heating the planet continuously at this rate. So what about volatile anesthetics? As I said, this is the picture of the flux of the energy. And to quantify, to what degree a molecule or a gas is a greenhouse gas. Actually, the question is, to what degree does it increase this transformation of infrared radiation in heat? So this is expressed as the global warming potential. It's a relative value, and its definition is the heating potential in a given period of 1 kilogram of a gas relative to 1 kilogram of CO2. So what does this mean? CO2 by definition has a global warming potential of 1. And for instance, methane gas, natural gas, CH4, has a value of 28, which means that 1 kilogram of methane will absorb as much energy as 28 kilograms of CO2 in a period of 100 years. Nitrous oxide will heat as much as 265 grams of CO2. One of the champions is sulfur hexafluoride. It's the gas that ophthalmologists use when they put gas in the eye. But of course, it's a very low amount. But anyway, 1 kilogram of SF6 will heat as much as 23 tons of CO2. So what determines this value? How do we get to this? Actually, it's only two numbers, two variables. First of all, of course, the added absorption in the infrared range spectrum. And secondly, the atmospheric half-life. Of course, a molecule needs to absorb infrared light in order to be a greenhouse gas. And all our volatile anesthetics do absorb infrared light. This is actually also how the sensors of our workstations work, by measuring the absorption of infrared light, so providing us the monitoring of the entitled values. And then we have, of course, so this is expressed as the radiative efficiency when we want to know how much, what is the intrinsic heating capacity of a molecule. So radiative forcing is the first concept. It is the change in energy flux in the atmosphere in watts per square meters. So if we add up the effect of all the additional greenhouse gases by humanity, so since the beginning of the global warming, we have a cumulative effect of radiative forcing of 1.64 watts per square meter. And then for a particular molecule, the radiative efficiency is a measure of the radiative forcing for 1 unit change in atmospheric concentration. This means that if we add, for instance, an amount of sevoflurane, so that the total atmospheric concentration of sevoflurane increases by 1 molecule of sevoflurane for every billion molecules of air, then how much watt per square meter will the Earth keep additionally? What will be the radiative forcing by adding 1 molecule for every billion molecules? And this radiative efficiency for CO2, for instance, seems a very small value, 0.0000013 watt per square meter. So this means that if we add 1 molecule of CO2 for every billion molecules of air, we will have an additional heat absorption of this value. For sevoflurane, this is a much higher value, you can see. If you divide them, then you see that 1 molecule of sevoflurane is 23,000 times more powerful greenhouse gas than 1 molecule of CO2. Because it's a large molecule, we can correct for the molecular weight. So 1 gram of sevoflurane is about 5,000 times more forceful than CO2. And of course, then the next important parameter is the atmospheric natural lifetime. A molecule that remains a long time in the atmosphere will capture much more heat than a molecule that disappears very fast. As sevoflurane has a lifetime of 1.9 years, for instance, isoflurane 3.5 years, desflurane 14 years, and nitrous oxide 109 years. So this lifetime, what does this mean? This type of curves we know all, of course, from pharmacology. And actually, the pharmacology of sevoflurane in the atmosphere is quite simple. It's a 1-compartment model, and this is the concentration after a certain time. So if we add a certain amount of sevoflurane, today, today it will have a concentration of 100%, and then tomorrow it will be a little bit less and less and less. This is described in this formula that we all know from pharmacology. And you see that after about 8 to 10 years, everything is gone. How long does the sevoflurane remain in the atmosphere? It's difficult to say and to put a number on it. So we use often two types of quantification. One is the atmospheric half-time or half-life, and the other is the atmospheric lifetime. What's different? Well, the half-life is quite simple. It's a time for a concentration to fall to half of its present value. This is one of the quantifications that we mostly use in pharmacology because it makes most sense. But in climate science, the atmospheric lifetime makes more sense. It's the Greek letter tau. So the natural lifetime is the average time that a molecule remains in the atmosphere, or put mathematically, it's the time till the initial concentration drops to 1 over E. And E is 2.718. So it is the time till the initial concentration drops to 1 over E is 36.8%. So in this case, you can see that the time it takes to drop to 50% is the half-life, and the time it takes to drop to 36.8% is the lifetime. What is so special about this 36.8%? That's traditional mathematics. If we in this case, we are interested in the area under the curve, because on day one, the amount of energy that will be captured is proportional to 100%, so the initial concentration. On day two, the amount in the atmosphere is a little bit less, so the amount captured will be also a little bit less. And if we want to summarize, to add up all the energy captured for all these individual days, we actually have to look at the area under the curve under this exponential decay curve. So this is expressed mathematically as the integral over from time point 0 to infinite of the concentration at any moment multiplied by the dt, by the time. But mathematically, we can also simply draw a rectangle with width tau and height 100%, and the area of this rectangle will be exactly the same as the area under the curve. So this makes it easy. If we want to calculate the total amount of energy captured, then we simply take the amount at the moment when we start, and we multiply it by the tau, the lifetime, and this is exactly the same amount of energy as if we would add up everything with this much more difficult formula. So this is why the atmospheric lifetime is more used in climate science. So then we have some data about sevoflurane, and if we want to compare it to CO2, we make the division actually. So if we, for instance, want to know the global warming potential of sevoflurane, then we want to know the heating potential in a certain period of 1 kilogram of sevoflurane relative to 1 kilogram of CO2. So we take this integral we had before, and we divide it by the same integral for CO2. So we know that the radiative forcing of 1 gram of sevoflurane is 5,245 times that of CO2. So for instance, if we would want to know the global warming potential over a time horizon of 1 day, and assuming that nothing has decayed over 1 day, then this value is 5,245. So the global warming potential over a time horizon of 1 day is 5,245. If we, but luckily, sevoflurane doesn't remain that long in the atmosphere. So the first day it will be 100%. And then the next day it will be a little bit less and less and less. So if we look over a 20-year period, almost all the energy captured by sevoflurane will be in the first years. So the total amount of energy captured, it's the area under the curve here, is this value. So it's actually the orange area. And if we take the same for CO2, so if we want the same amount of radiative forcing on day 0 of 1 gram of sevoflurane, we need 5,245 grams of CO2. So if we divide the area under the curve of the sevoflurane by the area under the curve of the CO2, we see that this is 13.4%. So this area is 13.4% of the blue area. And this means that we have to multiply this initial radiative forcing of 5,245 by 13.4%, which is 702. So the global warming potential over a period of 20 years is 702. If we take a time horizon of 20 years, if we would do the same calculations for a 100-year time period, then the amount of heat captured by sevoflurane will be exactly the same, because after 20 years there is no sevoflurane anymore, but we divide it by a much higher value because the blue area is much higher, and then the global warming potential over a 100-year period in this case is only 195. So this shows that the time horizon that is chosen to express the global warming potential can have an enormous impact. If we choose a 100-year time horizon, sevoflurane is only 195 times worse than CO2. If we take a 20-year time horizon, sevoflurane is 702 times worse than CO2. Another way to look at this is if we want to know how much CO2 we need to emit to have the same amount of global heating as 1 gram of CO2, we can look at the cumulative heat absorption. If we emit 1 gram of CO2 after 1 year, that will have caused global heating of about 100 megajoules. After 3 years, it's about 220 megajoules. But we see that it doesn't increase anymore after 9 years, let's say 7, 8, 9 years. So how long do we need to wait? So if we want to know after 20 years how much heat is absorbed by a certain amount of CO2, how much CO2 do we need to emit to have this same heat absorption, then we can, if we do the calculation for CO2, then we see that if we emit 702 grams of CO2 on this day 0, then after 20 years, the amount of heat absorbed will be equal. If we would make the same calculation for a 100-year time horizon, we see that the total amount of energy absorbed over 100 years will not increase for sevoflurane, but for CO2, because CO2 remains longer in the atmosphere, we need only 195 grams to reach after 100 years the same amount of heat absorption. So this shows again that the global warming potential, depending either if or you take a time horizon of 1 day, 20 years, or 100 years, has a great effect. But as I told you initially, one reason to take a time horizon that is not too long is because of, first of all, climate change is occurring now. And so if we would wait for 100 years to have the same amount of heat absorption by CO2 to compare it with our CO2, with our sevoflurane, that would grossly underestimate the immediate effects, because all this energy will be captured in the first few years and not after 100 years. And additionally, when we heat the planet now, we will activate positive feedback loops that cause additional heat absorption and additional greenhouse gas emissions because of CO2 emissions and methane emissions by permafrost and forest fires and so on. So this will even increase the amount of greenhouse effect because of our emissions of today. So this is one reason to prefer using a global warming potential with a time horizon of 20 years instead of 100 years. And these tipping points that are quite close. Here in this graph, you can see that even at heating of 2 degrees Celsius, and we are at this moment at 1.5, we see that already many tipping points are being crossed. And I think that in the USA and in Canada and in Siberia, they know what I mean by that. But then when these first tipping points are crossed, we will have additional increases in greenhouse gases that give acceleration of the greenhouse effect, and then cause other tipping points to be crossed, even if we stop emissions by humanity. So if we want to make a small calculation to know in a clinical situation what is the effect of anesthesia, let's say that I have a conventional classical anesthesia workstation and I use in 8 liters per minute with desflurane 6%. And I wonder what are the CO2 emission equivalents when I do this for 1 week, let's say 40 hours of maintenance anesthesia. So we have some problems that for the calculation. We, as anesthetists, use liter of gas per minute, but the radiative efficiency is expressed otherwise. So we have to do some calculations based on the universal gas law. We know if you put in all the variables that 1 mole of any gas equals about 24 liters of volume. So if we take all these constants that I told before, and we use it in the calculation, we have a fresh gas flow of 8 liters per minute at 6%. This is that much liter pure desflurane gas, which equals 0.0199 mole per minute, or 3.35 grams per minute. And if you multiply this by the global warming potential of desflurane, this is 23 kilograms of CO2 equivalents per minute. There are 2,400 minutes in a week. So this type of anesthesia emits about 56 tons of CO2 per week. If you would add nitrous oxide at 60%, and we do the same calculation, this gives an additional emission of 5.75 tons of CO2 per week. So yeah, these are numbers, but it's not also always easy to grasp this. How much is this? So it's useful to compare it to more conventional things that we know from daily practice as citizens. So for instance, if you would become a vegan, then that would save about 800 kilograms of CO2 per year. Or if you would avoid 1 round trip over the Atlantic by plane, that would avoid 1.5 tons of CO2 for 1 trip. So if we compare, for instance, let's say that I do everything in total intravenous anesthesia, and I work 2,000 hours in a year, then I emit about between 0.5 and 1 ton of CO2 per year. The propofol and the syringes and the plastic and also the incineration of all the waste together, less than 1 ton of CO2 per week. So if you compare this with an economical car and you drive 30,000 kilometers in a year, this is actually relatively low. So this is quite acceptable, I think, because this car would emit 3 tons of CO2 per week. If I would prefer driving a big Rolls-Royce or even a Hummer, a military Hummer for also 30,000 kilometers a year, then this is much more, of course, than my emissions as an anesthetist. But if I would use sevoflurane, even at end-tidal control, so minimal gas flow, this is already quite much more than driving of one of the most polluting cars available for citizens. And if I would use what we call low fresh gas flow, 2 liters per minute, then this is already almost double. But if I would add nitrous oxide, even in low flow, this becomes quite remarkable. And if I, for instance, would say, no, I work in Belgium like I do, but every weekend I fly to South Africa because I love it. And so I do this 52 times a year, then I am still more polluting than an anesthetist using low flow with nitrous oxide. Except, of course, if I don't use low flow and I use 6 liters per minute fresh gas flow and I add nitrous oxide, then that would be about double than doing all my plane trips. But if I would use desflurane at low flow, that would be even more. And if you do it at 6 liter fresh gas flow or at nitrous oxide, then it's even more. So simply, this gives a grasp of how much this is. The calculations are one way of looking at it. Comparing it to normal behavior gives an idea that we have a great responsibility. And I think it makes it quite obvious how to improve our impact. One small additional remark, of course, is if we use total intravenous anesthesia, what is the impact of the environment? Maybe propofol is polluting by itself in another way, not as a greenhouse gas, but because some of it comes in the wastewater, it may be harmful for aquatic ecology. So there has been written a lot of about it, particularly in anesthesia research, but actually there is very little to no scientific basis of it. So propofol is at reasonable concentrations by medical use, completely harmless for plant life, and has very limited effects on fish. It's very low compared to many other hospital pollutants. And very interesting, it has comparable pharmacokinetics as in humans. So also all higher organisms like fish and reptiles have renal clearance, and therefore there is no bioaccumulation in fish, just as in humans. As a matter of fact, propofol is routinely used in veterinary anesthesia and in aquaculture in many fish, of which I show some here. So since veterinarians use it routinely, this is another reason to be not too scared of it. In this Swedish study, where they looked at pharmaceutical residues in wastewater, you can see here, this importantly is a logarithmic scale. And here, these are all medications, all medications. So propofol is written here, and you see on this logarithmic scale, it is a value of 11, so 11 nanogram per liter. And you can see that many other medications have concentrations that are going to more than 10,000 times more. And it's quite particular or remarkable that we read a lot about potential harm from propofol on aquatic life, but nothing about potential harm of ibuprofen, for instance, or paracetamol. Also, from Switzerland study has done an investigation on the predicted risk quotient, so the real potential toxicity, and it shows that propofol has an extremely low risk, particularly compared to many other medications that we use routinely. Another question that is often pops up is that propofol would be extremely hard to destroy in an incinerator. That is actually completely false. You see the flash point, which is a measure of how easily something burns, when the flash point is, by definition, the temperature at which it burns spontaneously with a spark. So the flash point for propofol is 113 degrees Celsius. Compare this with even candle wax, which is already much higher, and the conventional plastics we use for a lot of things, both in hospital and at home. And all these, obviously, candle wax burns easily. So in any incinerator, propofol will be completely destroyed without any residues. One small additional remark, I have shown all these calculations based on what is really administered to the patient, but particularly for nitrous oxide, we have to be very aware of the fugitive emissions. It has been written in many publications already, and we have also in the hospital I work, in St. Jan Hospital in Bruges, we have investigated this, and actually far most of all the consumed nitrous oxide has actually escaped by through leaks. And this is general in all the hospitals that have published about it. So in our hospital, about 5,000 liters of liquid nitrous oxide was used, of which more than 90% was actually never used in a patient. And so all this has escaped to the atmosphere. And if you do the calculation, this represents the same as 1.7 million kilograms of CO2. This is more than what is emitted by 2 Starship launches. So this is really an enormous amount of CO2. So the most important message is, of course, that even if all the anesthetists in the hospital never use nitrous oxide anymore, but it remains available through the central distribution system, because we might eventually need it once, then you will have these fugitive emissions, which are truly enormous. So the message is, of course, that this should be investigated, and in, I think, most cases, if not all, that the central distribution should be stopped. And if you really want to have nitrous oxide available, to have it available only in bottles in case you need it, but not through the central distribution system.
Thank you. I think
so thank you for your attention.
Sorry. Thank you, Dr. Kalmar. We're going to move on and hopefully have some questions at the end. I'll keep this brief. Our last speaker is Dr. Jody Sherman, who's from Yale University. She serves on numerous national and